All right, today we're going to be talking about volumes of rotations when we revolve around axes other than the x or the y axis. So let's just jump in with an example, and then I'll talk through the rules I have up at the top. All right, so we've got R being a region enclosed by, I'm not sure why we're getting the weird double square root there, but that's just supposed to be square root of x minus 1. The vertical line x equals 10, and the x-axis, we want to find the volume when we revolve that region about the horizontal line y equals 3. All right, so we're going to start by constructing this, or drawing this graph. So let's see here. Square root of x minus 1 is going to be the square root of x shifted over 1 unit to the right. So when you plug 1 in for x, for instance, you will get 0, and then it's going to go off like that. The vertical line x equals 10. So x equals 10 is a vertical line, and that's going to essentially be one of our limits right there. And the x-axis. So looks like the region we're talking about here is this right there. Now you notice that these two functions here, or functions, the line and the function, they're going to intersect when x is equal to 10 or when y is equal to 3, because the square root of 10 minus 1 is the square root of 9, which is 3. So then my axis of rotation is going to be right along, or it's going to hit actually right where that point of intersection is. So here's my axis of rotation. So we're going to rotate around this. Let me just make an adjustment here. That's where my 3 is. So when I do a rotation about that, it's going to cause this lower area to flip and rotate around above that line. So in order to try to draw it, I'm going to attempt to mirror image that. So it's going to go something like this. And then the rotation is going to be like this. So if you notice, what we're dealing with here is we are going to be dealing with washer cross sections. And I know that I have washer cross sections because my region is separated from my axis of rotation. That always tells me that I'm going to have washers. So recall that when we have washers, we're going to use the volume formula, pi integral outer radius squared minus inner radius squared. And now because we're rotating not around the x-axis, but around an axis that is parallel to the x-axis, my thickness is going to be in the x direction, and therefore my integral is going to be an integral with respect to x. So based off of that and our previous conversation, we know that that function starts there at 1. We have this far limit of 10, so I know my integral is going to be an integral from 1 up to 10. Now the question is, how do we determine the outer and the inner radius? Well, we're going to determine the outer and the inner radius the same way we always do, and the same way we did before. And that method is to start at the axis of rotation and head toward the original graphed region. Let me zoom in on here. So here I am on the axis of rotation. I wanted that to be green. So here I am on the axis of rotation, and I'm heading toward the original graphed region. And as soon as I hit, bam, that is going to give me my inner radius. Now, notice that the inner radius is defined by the function square root of x minus 1, but it is not just equal to the square root of x minus 1, because the value of square root of x minus 1 would actually be, let's see, I need a different color here, would actually be this height right here. That is the square root of x minus 1. The green line that actually constitutes my radius is actually the difference between 3 and the function. So when we're in the plane, whenever you have a length that is bounded above by one function and below by the other, that length is found by subtracting top minus bottom. So that makes my inner radius 3 minus the square root of x minus 1. So that's my inner radius. Now let's talk about the outer radius. So the outer radius is going to be found similarly by starting at the axis of rotation and heading to the far end of the graph region. And you see that's really just 3. So that's going to be my outer radius, 3. So my outer radius is equal to 3. So I'm going to take my inner and my outer radii and I'm going to substitute them into the integral over here. Outer radius 3, inner radius 3 minus the square root of x minus 1, quantity squared, integral with respect to x. I see why this is determined to be a calculator problem, because even though we could do that, we could square out the 3 minus the square root of x minus 1, quantity squared, and do it by hand. It's going to be messy. So we're going to use a calculator to do that. But before I do that, I just want to come back over here and just point out something here. That it turns out, if you look at these values, that really my inner radius is simply given by my axis of rotation, which is 3, minus the function radical x minus 1. So minus, and actually let me call that, because it is the upper function. And by upper function, I mean the function that is defining the top of the region. And my outer radius, similarly, is given by the axis of rotation minus the lower function. Now, in this case, the lower function is the x-axis, also known as the line y equals 0. So what I'm saying is this outer radius is actually 3 minus 0, and my inner radius is actually 3 minus the function. The reason I'm bringing this up is because when we rotate around an axis other than the x or the y-axis, our inner and our outer radii are always going to take on this form, either the axis of rotation minus a function, or in some cases, it turns out to be the function minus the axis of rotation. But either way, it's going to be one of those forms. So that's a way you can check to make sure you have a reasonable radius. Although, to me, it still makes the most sense to just do what I did before, which is to start at the axis of rotation and head toward the function. All right, so let's go ahead and see if we can evaluate this function using my calculator. So in my calculator, I'm going to quit to the home screen, and I'm going to type in pi times math 9. That's going to get me my integral from 1 up to 10. And now I need to do 9, that's my 3 squared, minus, in parentheses, 3 minus the square root of x minus 1. So we have that quantity squared. Let's see, 9 minus 3 minus 1 squared with respect to x. Go ahead and hit enter, and we get 212.057 approximately. So 212.057. All right. Well, let's try another one. Number 2, a region R in the first quadrant only is enclosed by y equals x cubed and the cube root of x. Find the volume obtained by revolving the region R about the line x equals -2. Okay, so let's see here. The cube root of x, x cubed as a function comes up like this and then over like that. But we're only in the first quadrant, so I'll ignore that part. And then the cube root of x, similarly, comes in this way and then curves out that way. Again, I'm only in the first quadrant, so I'll ignore that part. And then I'm going to go ahead and erase out these parts that we don't want because we can see that the region is defined right there. And then what I'm going to rotate around this time is the line x equal to -2. Now, x equals -2 is a vertical line. So draw it in just about like that. So there is x equals -2. Now, if I rotate around that line, I'm going to end up with a mirror image of my original region. In fact, let me just go ahead and shade my original region so that we have that. Whenever we determine pretty much everything, we're going off of the original region. So this is a 2-unit distance. So I'm going to extend out my x-axis here. And so this will start also at about a 2-unit distance. And then it's going to, let's see. It's going to be challenging to draw. It's going to curve this way and curve that way. So something like that. And then we're going to get this big rotation here. So once again, this is going to be a hollow object because of the spacing between the axis of rotation and the region. And so we're going to have this inner radius and we're going to have an outer. Try that again. And we're going to have an outer radius. Now, because I'm rotating around a axis that is parallel to the y-axis, my integral has to be with respect to y. So when I set up my volume, I'm once again going to have washer cross sections. So outer radius squared minus inner radius squared. This time, though, my integral is going to be with respect to y. Now, because my integral is with respect to y, my functions have to be functions of y. Right now, I have functions of x. So I need to take each of my two functions and solve them for x. So let's see. This function right here, which was x cubed, if you solve that for x, you're actually going to get the cube root of y, also known as y to the 1/3. And this function, which was the cube root of x, is actually going to be x equals y cubed if you solve both sides for x. Now that's important because when I go to find my inner and my outer radius, I start at the axis of rotation, I head toward the region, and the very first thing I hit is the function y cubed. So that tells me that my inner radius is not going to be given by y cubed because, once again, y cubed is actually this length right here. What I'm really dealing with is I'm dealing with y cubed plus a little bit more. So take that y cubed value and add this to it, which is really just 2 because this is the line y equals or x equals -2. So this length across here is 2. This length right here is 2 plus y cubed. Inner radius is really 2 plus y cubed. outer radius, similarly, is going to be 2, that's that length right there, plus the value of the farthest to the right function, which in terms of y is y cubed. Now, once again, I want to show you that these are actually of the form function minus axis of rotation and function minus axis of rotation. So the previous one was axis of rotation minus function. These are the form function minus axis of rotation. The inner and the outer radii are always going to be one of those two things, either axis minus function or function minus axis. All right, so let's take those inner and outer radii and substitute them in up here. We are going to need limits of integration. Outer radius is y to the 1/3 plus 2. We'll go ahead and square that. And inner radius is y cubed plus 2. Square that. Integral with respect to y. Now we need limits of integration. So our original functions were x cubed and cube root of x. So they both start at 0 here, and the other place where cube root and x cubed are the same is at 1. And if you plug 1 into either one of those, you're going to get a height of 1. Since this is an integral with respect to y, I need to look at the values that define the interval along the y-axis. And in this case, it's the same x or y. They're both 0 and 1. So 0 up to 1. Now again, when I created this problem, I think I thought we could do it without a calculator. And while we could, I certainly don't want to. So I'm just going to leave it at that. If you wanted to use your calculator, go ahead and do that. You should be able to. I'm going to go ahead and leave the answer just like that. You could plug that in your calculator if you want to. All right, last one. We've got R being the region in the first quadrant bounded by the graph of y equals sine of x, the x-axis, and the vertical line x equals 1. We want to find an integral expression that gives the volume of the solid generated when R is revolved around the vertical line x equals 1. Okay, so let's see here. We've got sine of x, the x-axis, and the vertical line x equals 1. Okay, so the x-axis is, of course, this. Vertical line x equals 1 is right there. And then the sine function, we know, goes from 0, and then it goes up from there. So it's going to, I guess do something like this. The sine would reach its peak at pi over 2. Pi over 2 is about 1.57, so 1 is not quite there yet, so it's still on its way up. So that is the region bounded by sine of x, the x-axis, and the vertical line x equals 1. And now we're going to rotate that around the vertical line x equals 1. So if we do that rotation, we're going to end up with something that kind of looks like a mouse. And I want you to notice that there is no separation. There is no separation between the axis of rotation and the region. So what that tells me is I'm going to have solid disk cross sections. So volume is going to be given by pi r squared. Now we're rotating around an axis parallel to the y-axis, so that's an integral with respect to y. Let's determine what our outer or what our radius is. Our inner, we know we're not going to have an inner radius because if you start at the axis of rotation, you head to the region, you're already there. That tells me my inner radius is 0. The outer radius is going to be what happens when I get to the far end. All right, so we need to talk about what is that length. But because we're doing an integral with respect to y, I need to rewrite my function. So this function right here, which I know is sine of x, I now have to solve it for x. And I'm going to get the inverse sine of y. So if y is the sine of x, then x is the inverse sine of y. Now, the radius is not the inverse sine of y because, once again, the inverse sine of y is actually that length. So what is this? It's 1 minus that. So my radius is going to be 1 minus the inverse sine of y. So pi integral 1 minus the inverse sine of y, quantity squared, integral with respect to y. And now what are the limits? Well, obviously we need y limits. So the lower end of that region is defined by 0. The upper end of that region is defined by whatever this is. Now, what is that y value? Well, it's what you get when you plug 1 into the sine function. In other words, it is sine of 1. Now, I don't know what sine of 1 is. I could get a calculator out to find it, but I don't really need to, because all we were asked to do is to find an integral expression that gives the volume. We don't actually have to find the volume. So there is my integral expression that gives the volume of this region when rotated around the line x equals